Thank you for inviting me to the conference. I'm very grateful for that. And my name is Jaakko. I'm from Aalto University, Finland. And today I will talk about my research that is related to extreme value theory. And first I try to give like a very general description about the themes of our research. After that, I review some stuff about univariate extreme value theory and actually mostly about habitat distributions, because that has been the focus on our research, at least for now. And after that, I speak more specifically about the actual research projects. Okay, but yeah, we have had already a couple presentations about extreme value theory, so it's concerned about extreme events. And here are some applications provided by the extreme value theory. So specifically, I will talk more about extreme quantile estimation today because it's related to one of the projects. And there's a lot of literature about univariate extreme value theory. I think statistical developments related to that started in 1970s already, but currently the focus is on multivariate and infinite dimensional cases. And one way to, so this point one tries to describe one way to extend univariate extreme value theory to multidimensional cases. So in extreme value theory, the approach often is that you assume some regularity for the tail, and then one approach to extend univariate extreme value theory is somehow like directly generalize this kind of regularity assumption for the tail in multivariate and infinite dimensional cases. So for example, this multivariate maximum domain of attraction is this kind of generalization of the regularity condition for the tail. But we have a bit different perspective in our research. So instead of thinking this approach one directly, what we do is we take the multivariate or infinite dimensional random variable, and then we try to reduce it to univariate random variable. So for example, you can take the norm of the random variable, and now the norm will depend on the context where we work. Of course, more generally, the function can be any functional that you take, but currently our research has focused on the norms. Sometimes these two approaches are equivalent, and one benefit in that case for the approach 2 is that then this approach 2 can provide more simple ways to estimate stuff, for example. Okay, then to the habitat distributions, and actually the purpose of this section is actually to just introduce the extreme quantile estimator for the univariate case. So if we want to do quantile estimation, then, and as I said, in extreme value theory, the approach is to have this kind of regularity condition for the tail. Then we maybe want to formulate this regularity condition in terms of quantile function. However, the quantile function is not quite the right object, but we define this kind of tail quantile function, u, corresponding to some distribution f. But yeah, it just resembles quantile function a lot. So u of 1 divided by p is just 1 minus p quantile. So if you have, if you take value of the function u for very large t, it will be just quantile on the right tail of the distribution. Okay, and now here's this regularity condition. So we restrict to habitat distributions because that's what our research has focused on currently. But there are more general frameworks also. So we say that a random variable is heavy-tailed if the corresponding tail quantile function is regularly varying with positive index gamma. So there's this exponent gamma. In the definition of regularly varying functions, the index of regular variation can be generally any real number, but for heavy-tailed distributions, we restrict to positive indices. And what's kind of the intuition about this definition? Well, actually, U function corresponding to Pareto distribution is just t to the power of gamma. So then regularly heavy-tailed distributions have function U that is equal to the function U of Pareto distribution up to some function L. And now this L satisfies this kind of limit relationship that we have here. And intuitively speaking, they are kind of like constants. You don't have to care about them too much in the asymptotics. And here's the meat of this section, so the definition of extreme quantile estimator. It's hard to see here, but actually the motivation and how this estimator is constructed is with the definition of regular variation on the previous slide. So when we talk about extreme quantile estimation, we want to estimate 1 minus p quantile for some very small p. And I have denoted that p depends on n because on asymptotic results, we want that p goes to 0 at some rate as the sample size increases. And if we look at the estimator, there are some components. There's the n minus kth order statistic. So you can think it like so that you use the data somehow in the estimation, now in the form of the order statistic, and then you extrapolate outside the sample somehow. And now how the extrapolation is done is determined by this index of regular variation or the extreme value index gamma. But of course, we have to estimate that also. So there's this gamma hat, which is some estimator of the extreme value index. Then there's also this parameter k. So k kind of determines where the tail of the sample begins. And this is something that user has to choose. In asymptotic results, we again let it depend on n, and in such a way that k is somehow small compared to the total sample size n. So in extreme value theory, it's common that you kind of use the tail observations in the estimation. But of course, in practical cases, you have to choose k somehow, and that's not necessarily easy. It's actually a topic of current research still, how to choose k optimally, because the estimation procedures are often not robust under the choice of different k's. Yeah. But now to the actual projects. So the first project is related to elliptical distributions and this kind of multivariate extreme quantile estimation. So here's a figure that tries to illustrate kind of the point of this project. So let's assume that we have an elliptical distribution with density. Then the density contours are elliptically shaped. And first thing that we have to do is define what this kind of quantile in this case. Well, for elliptical distribution, there's a very natural way to define multivariate quantile, or what I actually call here quantile region. So what we want to do is to find density contour in such a way that the complement of the ellipse given by the density contour includes p probability mass. Then I call that p quantile region. And now in the extreme value theory context, again, we wish that the p is somehow very small compared to the sample size. So what happens in practice is that you have no observations lying on the quantile region that you want to estimate, or you have just very few observations. And then if you try to estimate this kind of quantile region with something motivated by sample quantile, let's say, the estimation fails because you cannot extrapolate outside the sample, but our estimator works better in this kind of cases. And now here's the formal definition for elliptical distributions, or actually this is not like original definition, but it's like this kind of stochastic representation for elliptical distributions. And easy way to get like intuition about this is to think how this can be used to simulate observations from elliptical distributions. So let's start from right to left. So first we have this random variable S, which is uniformly distributed over unit sphere. So first you simulate observation from unit sphere. Then there's this matrix lambda that is related to this other matrix sigma. So sigma is called the scatter matrix. So now you have this observation on a unit sphere, and then you map it to some ellipse. So this scatter matrix sigma determines kind of the shape of the density contours. After that, we multiply or kind of scale the ellipse where the observation lies somehow. So there's this non-negative univariate random variable R, or what I call the generating variate, that scales the ellipse. And lastly, there's the location vector of the elliptical distribution. And now this generating variate is very important for us. So there's this kind of theorem that if elliptically distributed random variable x satisfies this kind of multivariate regular variation condition, so one of these generalizations of this regularity condition for multivariate cases, then that is equivalent to the fact that this univariate random variable generating variate is regularly varying. So in essence, this univariate random variable encodes all the information about the tail. So that's what we want to work with when we do extreme value theory. And again, from the point of statisticians, you only observe the multivariate sample of multivariate observations. So you want to extract the generating variate somehow from the sample. And for that, you can use the Mahalanobis distance. This follows straight from the representation on the previous slide. However, again, from practical point of view, you don't know the true scatter and location of the distribution, so you have to estimate them. So actually, you have this kind of approximated sample or sample of approximated generating varieties or something like that. And so if we kind of go back to the very beginning of presentation, I told that we do extreme value theory with the norm or some functional of the original data. And in this case, Mahalanobis distance is kind of this kind of norm is the correct way to think about this in this context of elliptical distributions. And here we also see like another thing that's kind of related to our research, that often we introduce this kind of approximation errors that have to be taken into account in asymptotic results. Okay, now the actual estimator. So first of all, the quantile region that I explained a couple slides previously has a very simple expression for elliptical distributions. So this RPN is just 1 minus p quantile of the generating variate. And now when we construct the estimator, we just want to estimate the location and scatter. And we have to estimate this quantile. And now surprise, surprise, the quantile is estimated with something that resembles the extreme quantile estimator, but we have now replaced the true sample of the generating variety with these approximations, and also for the estimator of the extreme value index gamma, you have to use the R hats, the approximated observations. And in this project, we provide consistency results. So the most important assumptions are that the generating variety has to be heavy-tailed, and then Pn goes to 0 as n goes to infinity with some rate. There are, of course, other technical conditions. For example, estimators of the location scatter have to be square root of n consistent. And this is how the consistency result looks like. And at least to my eye, it's a bit exotic. So we look at the probability mass on the symmetric difference. And now the symmetric difference means the points that lie in either of the ellipses, but not on the intersection. And we divide with this Pn, and this is necessary because the thing that we estimate depends on the sample size. So as the sample size increases, the ellipse that we want to estimate, it just blows up. So if we would not divide by Pn, then empty set would be a consistent estimator. And we also provide this kind of equivariance property under affine transformations, which means that you can apply this affine transformation to the data first and then estimate, or vice versa. You can first estimate and then apply this affine transformation to the estimated region that you get. And it doesn't matter, the order doesn't matter, you get the same results. And this basically it's very easy to prove. It follows from the affine invariance of the Mahalanobis distance. Then a couple words about this other project, and this is related to functional data setting. So as in this case, we assume that we have realizations of some stochastic process that lives in LP space. And again, we are interested doing extreme value theory with the norms. So in this case, LP norms. And then we hope that LP norms reveal something about the extreme behavior of the process. For example, it can describe if we think about L infinity norm, it can describe like the worst losses while you trade something, and your observations are like the stock values, how they fluctuate during a trading day or something like this. And okay, then you can, for example, estimate the extreme value index. If you have these norms available and you assume that they are heavy-tailed, so there's really nothing special to do here. However, in reality, you rarely observe, or the stochastic realizations are rarely available as a whole. But for example, you only have the discretized versions of the realizations. And then you have to, again, approximate the norm. And if we use this kind of discretized version of the process or the simple process, then actually the norm of that process, it's just the kind of Riemann sum approximation of the integral that we consider. And then when we estimate the extreme value index, you have to replace the real norms with the approximated ones. And yeah, by the way, this estimator here, it's called the Hill estimator. It's one of the most common estimators for the extreme value index in the heavy-tailed case. I forgot to say that. Okay, and then we have this kind of theorem that actually applies in more general contexts. than the LP case. So let's say that we have a random variables that are heavy-tailed, and then we want to approximate them somehow. Then this theorem says that, okay, if the maximum error of the approximations doesn't blow up too quickly, then we have consistency for the extreme value index estimator in the slides. Also similar theorem holds for the extreme quantile estimator. Okay, but this is like very high level. We want to most probably say something about this maximum error. So here's an example that I considered in the conference article. So, and similar settings are considered in this project too. So you want to have some kind of regularity for the process. So now if we have, for example, a fractional Brownian motion, it gives a nice continuity, and then we divide it with this kind of thing that includes the chi-square distribution. And now the thing that we divide it with gives the heavy-tailedness for the process or for the norm of the process. And now the thing that we want to go to zero looks like this. So you see there's this m, which is the number of discretized points that we have. Then there's this gamma that determines the heavy-tailedness, and then there's this h that gives the like the Hölder continuity for the fractional Brownian motion. So what this says that if you have very heavy-tailed norm, then you have to have a better continuity assumption or have more those discretized observations to kind of fight against that. So yeah. And of course, I spoke only about heavy-tailed case, and that's what the research has focused on, but the wish is also to kind of think about the light-tailed and short-tailed cases in the future. But yeah, thank you. I think that was it for me.
Thank you. Thank you for your presentation, Jaakko. We have again, say 3 minutes to 3 minutes for questions. Please.
Hi, first of all, thank you, Jaakko, for the nice talk. You have mentioned several times Hill estimator, which is common in extreme value theory. However, my question is concerned with the other also common estimator, the Pickens estimator. So have you considered that instead of the Hill estimator in this context?
Not yet, so that's kind of what we wish to consider then when we include light-tailed and short-tailed frameworks. And the idea was actually with this second paper that I talked about, idea was to consider just the like domain of attraction framework straight away and include heavy-tailed, short-tailed, and include all the cases like simultaneously. But with preliminary calculations, it appeared that actually it's the approximation error and how it has to behave is a lot more intricate problem in the short-tailed and light-tailed cases. So that's why we kind of we will consider it in future, but not yet. So yeah, hopefully that answered the question.
Yes, thank you very much.
Thank you. Anybody else? I'll just shortly additionally ask, so in terms of the heavy-tailed behavior, does this include any type of behavior, say power law or anything similar? Is this, can be generalized to any type of power law behavior in the random variable?
Yeah.
And for both cases, I think we have two different, right?
So wait, now you have to remind me the power law. So is it this kind of law or something different?
Approximately, yeah.
Yeah, so is is Pareto distribution power law. I just don't remember the meaning. So yeah, yeah, it's exactly the kind of thing that I think the definition of regular variation tries to kind of say that. Yeah, we consider this kind of power law type of distributions.